This is the second lecture on the immune system. There's different cells involved with the immune system, and we'll talk about these. There's B lymphocytes, T lymphocytes, and antigen presenting cells. We'll discuss the differences in these type of cells momentarily. First, let's talk about the lymphocytes. The lymphocytes are the warriors that fight against infection. Just like any other warrior, they need to be trained, they need to go to school, they need to have education to learn how to be the fighters that they are. So these are the steps for the preparation of the lymphocytes to be the pathogen fighting warriors that they are. First step is they have to be born. Like all blood cells, lymphocytes originate in the red bone matter from hematopoietic stem cells. So all the lymphocytes are born in the bone marrow. Then to go to school, they go one or two places. They either go to the bone marrow, stay in the bone marrow, or they go to the thymus. Cells that stay in the bone marrow for maturation are called B cells. Cells that migrate to the thymus for maturation are called T cells. In their school, there's two subjects they learn: immunocompetence and self-tolerance. Immunocompetence is when the lymphocyte learns to recognize a specific antigen by binding to it. That's what lymphocytes are supposed to do. That they're looking for antigens. Antigens are parts of the foreign bodies and foreign bacteria that produce antibody responses. So lymphocytes need to be able to recognize an antigen by binding to it. They also learn the subject of self-tolerance. Self-tolerance is basically learning to ignore the body's own antigens, because every cell has antigens. You don't want lymphocytes reacting to your body's antigens, because then it would react against natural normal cells that you in the body. Lymphocytes want to learn to react against foreign or non-self antigens. So they're educated in the bone marrow and in the thymus. Now, after they've had education, they haven't had experience yet. They're still naive. The antigens are called naive. So then they have to go to where the action is. They go to lymphoid organs and circulation so they can be exposed to antigens. Again, they've gone to boot camp, they've gone to basic training to learn how to fight antigens, but they've not really encountered any antigens yet. That's why they go to the lymphoid circulation, or lymph nodes, or the spleen, the different lymphoid organs. Because when they go there, then they increases their chance of encountering an antigen. Then when they meet their first encounter with antigen, the lymphocyte undergoes changes so that the lymphocyte will complete its maturation after it receives the contact by an antigen. Here in this diagram, you can see the antigen here represented by the red star, and here's the lymphocyte with the antibodies. So antibodies are formed that match this antigen. And now the goal is you want to create more of these antibodies so that you can fight off more of these antigens. That's in the proliferation and differentiation stage. So these activated lymphocytes, after they've encountered their antigen, they become activated and they start to proliferate, and they produce exact clones of themselves. These clones are the effector cells that fight infections. Some of the clones remain as memory cells, so that they can respond to the same antigen more quickly a second time. So if you're exposed to that pathogen at a later time in your life, you have the memory cells that are there to remember how to form the antibodies toward it. The B and T memory cells and effector T cells circulate continuously. Here's an overview of the difference between B lymphocytes and T lymphocytes. Basically, the thing to remember is B lymphocytes have humoral immunity. Humoral just means body fluids, and so basically humoral immunity is referring to the antibodies that are produced against certain antigens. So antibodies are secreted by the B lymphocytes, and their primary targets are extracellular pathogens, bacteria, fungi, parasites, some viruses that are in extracellular fluid. Their site of origin is the red bone marrow. Their site of maturation is red bone marrow. The effector cell of B lymphocyte is called a plasma cell. And compared to T lymphocytes, they have cellular immunity, not humoral but cellular. They do not secrete antibodies, and their primary targets are intracellular pathogens. Once the pathogen is got inside the cell, then it's going to be almost invisible to the antibodies. The antibodies they react to points on the outside of the foreign cell. Once something's invaded the cell, like a virus has invaded the cell, or a cancer cell that's on the outside looks like a normal cell, but inside is cancerous due to its unregulated growth. That's where T cells come in, because they can detect those cells and kill the cells. The T cells originate in the red bone marrow, and they're mature in the thymus. They form cytotoxic cells, helper T cells, or regulatory T cells. We're talking about lymphocytes. The next cell is antigen-presenting cells. Antigen-presenting cells basically makes an antigen easier to be recognized by the T cells that need to recognize them to form antibodies. So antigen-presenting cells, first of all, they engulf the antigen, and they start to digest the antigen, and they break it into different parts. But what they do is they put fragments of the antigen on their own surface where T cells can recognize them. It's like an antigen amplifier. Like they take the antigen and then they spread out the parts of the antigen on their own surface of the antigen presenting cells, so that they're presenting the antigen for the immune system to see. Have the picture of a race car driver, because it kind of reminds me of the antigen presenting cell with all these patches on it on board, so you can see who the sponsors are. Same way the antigen presenting cell puts parts of the antigen on its surface so that they can be recognized. When the B cell is activated by its encounter with an antigen, the lymphocyte rapidly reproduces itself to form an army of identical clones with the same antigen specificity. Some of these clones become effector cells by fighting infection. Some become memory cells. The effector cells of B lymphocytes are called plasma cells, which are antibody-secreting machines. So the antibodies are formed by the plasma cell, which is the effector cell it's basically a type of B lymphocyte. There's a primary and secondary immune response. A primary immune response is basically what we've described in the slides that came before this, where you have the lymphocytes exposed to an antigen and then matures and differentiates and clones itself and produces other antigens. That's a primary immune response. It typically takes about 3 to 6 days after antigen exposure before it can mount an immune response. The peak levels of plasma antibodies are reached in about 10 days, and then the antibody levels decline. Here's a diagram of the primary immune response. Again, the antigens are represented by the red star. The lymphocytes are represented by these purple cells. They recognize the antigen, and once they recognize an antigen and bind to the antigen, then it causes change in that lymphocyte. It starts to proliferate to form a clone, and at this point they're activated B cells forming a clone, and they develop into plasma cells, which secrete the same shape antibody that is needed to recognize this antigen. So it produces antibodies that are all specifically designed for this particular antigen. Once these antibodies are floating in the bloodstream, they encounter the antigen, and then that's called opsonization, and that makes them prime targets to be phagocytized by the phagocytic cells, and therefore eliminated from the body. So all this is a primary response. There's a secondary immune response. Now, what happens if let's say later that same antigen appears again? Let's say the antigen is the flu virus, and the first time you had the flu virus, you you built antibodies to it, and you fought the flu. Let's say you get the same strand of flu virus at a year later, where you have those memory cells which remember how to form antibodies for that particular flu virus. And since it's seen it before, the response at this on the secondary immune response is much faster, much more effective response than the primary immune response would be. Antibodies peak in 2 to 3 days at much higher levels. The antibodies bind with greater affinity, so they're more efficient antibodies. They're more dangerous to the antigen, and they can remain high for weeks to months. And here's kind of a diagram that shows that. The first top part is basically the primary response. Secondary response. First of all, the primary response, it produces the effector cells, these plasma cells that secrete antibodies, but also makes a memory cell, which memory cell just stays around, and it's programmed to release these antibodies based on exposure to this antigen. So at a later time, years later, the body's exposed to that antigen again, these memory cells are able to quickly mobilize into and become plasma cells, which secrete all these antibodies that are designed for that antigen. So the second time you're exposed to that antigen, you have a much more rapid immune response and a much more effective method of getting rid of the specific antigen. This chart shows the response to 1 or 2 antigens. Let's say on day 0, this is days here, and this is the amount of antibodies produced. On day 0, you're exposed to antigen A. Well, notice it takes about 5 or 6 days before you see any antibodies to antigen A. Then you start to have the antigen A antibodies start to build up, and it has an increasing level up to a point that it levels off, and then the antibodies taper down. But let's say this is a later time. It could be years later or months later. You have a second exposure to antigen A. Since the pump has been primed for that antigen already, you have a much more rapid response. See how the rapid response is a much higher response. That means there's a lot higher amount of antibodies this second time exposure. Second time exposure is much higher antibodies, and it lasts longer. So this secondary response is a more effective response to the antigen. Now notice if you're exposed to a different virus, let's say this is for the flu virus, and this is the hepatitis virus, for example. It's a unique virus, and it has to have the same process. Its first exposure, your first exposure to the second virus, your first exposure to the second antigen will produce antibodies in a similar manner that it did for antigen A. Now, if later on you're faced with antigen B again, then you have a response like this. Just note that the secondary response is a faster, larger, and more effective response than the primary response. Active humoral immunity is when your own B cells encounter antigens and produce specific antibodies against them. Okay, that's what we've talked about so far. Your B cells encounter an antigen and produce antibodies which are made to order, special order, to be tailor-made for that particular antigen. The active humoral immunity can be naturally acquired or artificially acquired. Naturally acquired refers to the response to bacterial or viral infection. This is what happens when you get the flu or get a cold or you get some sort of viral infection or bacterial infection. You go through the immune response, you make antibodies to this pathogen, and then you're ready to fight the infection. But the active humoral immunity can be artificially acquired. This is getting a vaccine of a dead or attenuated pathogen. A vaccine is when you're injected or exposed to a pathogen or an antigen that's similar to the antigen causing disease, but maybe it's not as it may be weakened. It may be a dead virus or attenuated virus. When Edward Jenner came up with the smallpox vaccination, the smallpox was killing people and it was very deadly. But he found that there's another similar disease called cowpox that was very similar to smallpox but not as deadly. And it was similar enough that when he inoculated people with the cowpox, it produced a sorry for that telephone interruption. Let me pick up where I left off. So Edward Jenner found this cowpox, which was not nearly as harmful to the person as smallpox, but it was close enough to smallpox, so it tricked the body into making antibodies that would also react to smallpox, so they could have exposure to this less virulent pathogen and still have a good immune response against the main disease, smallpox. This is what is referred to here as this artificially acquired active humoral immunity. So it's like you have an immunity against the smallpox, for example. It's artificially acquired because you didn't get exposure to smallpox to get this immunity. You got exposure to another virus, cowpox. Or as used as an example, it could be from anything with a vaccine can have the same results. Now there's passive humoral immunity. What we talked about before is active. Now passive humoral immunity is ready-made antibodies are introduced into your body. So you're given antibodies from some other source into your blood system, and these antibodies are then there to fight off antigens. But your own beta cells are not challenged by antigens, so there's no exposure to antigen that causes these antibodies to be made. These antibodies are made somewhere else and are injected into your body. There's no immunologic memory that occurs because, again, there's no maturation, there's no education of your own lymphocytes to form antibodies. These antibodies are formed somewhere else and they're injected in your body. This can occur naturally or artificially. Naturally, example of a naturally acquired, but think of a situation where naturally you would receive antibodies from another source to fight off infection. Well, when you're in your mother's womb and you do receive antibodies through the placenta, and this can react to certain types of infection. Or also when you're a newborn baby, you can receive antibodies through breast milk that can go to fight infection, and it gives you a naturally acquired passive humoral immunity. It's called passive humoral immunity because your own B cells do not react to the antigen. And it's artificially acquired is when you're injected with a serum of antibodies. Example, this is snake bites. You give it antivenom. All antivenom is antibodies directed towards the snake venom. You're injected with these antibodies, and it helps fight off the antigen. Helps get rid of the antigen. Another example of this is we talked about the blood, the hemolytic disease of the newborn. When a mother's Rh negative has an Rh positive baby, and she's given Rogam, which is basically antibodies to the Rh factor. That's an example of artificial acquired passive immunity. So this block diagram shows the four conditions. Humoral immunity. Humoral immunity basically has to do with antibodies. It can be active or passive. Active can be naturally acquired or artificially acquired. Passive can be naturally acquired or artificially acquired. You need to know the difference in these. And if I give you a situation where I describe one of these situations, you need to be able to tell whether it's active, naturally acquired, active, artificially acquired, or passive, naturally acquired, passively, artificially acquired. Another name for antibodies are immunoglobulins. These are proteins that are floating in the blood. They're secreted by the plasma cells, and they're capable of binding specifically antigens. They're capable of binding specifically antigens detected by the B cells. There are 5 classes: M, A, D, G, E. Remember MAGE. Here's a diagram of a typical antibody. There's a variable region and a constant region. The constant region are the stem and the first part of the heavy chain and light chain here. But towards the end, there's the antigen binding site. This is variable. This is variable depending on what antigen is exposed to this antibody. So this is variable here, and this is antigen binding site made of these two parts of the chain. It's on both ends here, very variable. The stem region, or the constant region of the antibodies, is what determines the class of antibodies, whether it's M, A, D, G, or E. And the best way I think to give you an illustration of the difference in antibodies is, we talked about how the antigen, or how the lymphocyte is exposed to an antigen, and therefore it proliferates and becomes a plasma cell and produces more antibodies. The antibody, the part that recognizes the antigen, is let's see here, is on this IgM. It's first responder. It's the receptor site for the antigen. It's on the B cell membrane. It recognizes the antigen, and then the lymphocyte goes into this maturation cycle where then it produces other antigens that have the same N to recognize the antigen as the original antibody did. So these other classes of antibodies are antibodies that are produced by plasma cells that have the same pattern to recognize the antigen that the original B cell had to recognize antigen in the first place. Let's look at a summary of the antibody and antigen reaction. First of all, antigen-antibody complexes do not destroy the antigen. It prepares them for destruction by innate defenses. Having an antibody attached to an antigen puts a target on its back, basically, so it's seen and recognized by the phagocytic cells. Antibodies attack extracellular pathogens, such as bacteria, free viruses, or soluble foreign molecules. Antibodies attack pathogens that are free floating in the blood, and they do not invade solid tissues unless a lesion is present. However, antibodies can act on intracellular if it attaches to a virus before it enters the cell. Then the antibody can activate cellular, intracellular mechanisms to destroy the virus. But generally, the antibodies work extracellularly. The cellular immune responses. The T cells are suited for cell-to-cell interactions. T cells provide defense against intracellular antigens. Remember, T cells are killer; they kill the cells. So these would be cells that are infected with the virus. So the virus is kind of inside the cell and is hidden from the regular antibody recognition. But the T cells can recognize these infected cells and kill them. When activated, B cells become plasma cells to produce a large amount of antibodies, but T cells can become multiple effector cells. They can become helper T cells, cytotoxic T cells, regulatory T cells, or memory T cells. They have one of 4 types of effector cells. Helper T cells play the largest role and the most widespread effect of any cell type on immunity. They do so many things. The helper T cells activate the B and T cells. They induce the B and T cells to proliferate. They basically make the adaptive immune system response happen. They activate cytotoxic T cells. They activate macrophages to become potent killers. They promote inflammatory responses against extracellular microbes. They do a lot to enhance the immune system. They're crucial to the immune system. Another effector cell for T lymphocytes are cytotoxic T cells. These are T cells that they're created to, with their main function is to kill other cells, mainly cells infected with viruses or cells with intracellular bacteria or cancer or foreign cells introduced into the body. So these destroy cells. Regulatory T cells, they tend to dampen the immune response. They kind of keep the immune response from getting too aggressive. They suppress self-reacting lymphocytes in the periphery and therefore prevent autoimmune disease. Part of the schooling of lymphocytes is self-recognition of it recognizes its own body's antigens and not to attack them. But when the lymphocytes antibodies attack antigens from its own body, then that results in autoimmune diseases. These regulatory T cells help prevent autoimmune disorders. Talk about some specific infections. AIDS, acquired immune deficiency syndrome. This is caused by the HIV virus, and the target for the HIV virus is the helper T cell. Remember, the helper T cell does so much for the immune system. If you knock the helper T cells out, you basically cripple your immune response, and you cripple your immune capabilities, so you're more likely to get infections. And when AIDS first discovered, they noticed that people were getting infections that normally were not very common. They were getting pneumocystis pneumonia, Kaposi sarcoma, things that are normally not found, but since they had an impaired immune system, the people were susceptible to getting these infections. And so AIDS was initially seen to have just very unusual and very rare infections that would all of a sudden become more popular, more prevalent. It's all because the helper T cells were impaired and were not able to enhance the immune system as they normally should. Again, AIDS is caused by the human immunodeficiency virus, or HIV, transmitted via body fluids. It destroys the T helper cells and suppresses cellular immunity. Autoimmune diseases. And if you're a lymphocyte and you're out to fight antigens, you want to fight fight the foreign cells that are introduced to the body. You want to protect the body against foreign invaders. What you don't want to do is you don't want to turn your cell phone to your own body cells. When T cells become sensitized to antibodies from its own self, antigens from its own body, that's what produces autoimmune diseases, when the basic body attacks its own tissues. Here's some examples of autoimmune diseases. There's multiple sclerosis. It's an autoimmune disease in which the myelin of the white matter of the brain and spinal cord are targeted by the immune system. And myasthenia gravis is when the neuromuscular junction is targeted by the immune system. Graves' disease is when the thyroid gland is targeted by the immune system. Type 1 diabetes is when parts of the pancreatic beta cells are targeted by the immune system, and so on. Glomerulonephritis is kidney damage due to autoimmune disease. Rheumatoid arthritis is joint damage due to autoimmune disease. There's hypersensitivities. You can be sensitive to things that normally would be harmless to the body, such as pollen or animal dander. But the immune system can be overactive and react to this exposure in a dramatic way. There's type 1 hypersensitivity, which is immediate hypersensitivity. This can occur only seconds after contact with an allergen. An allergen is something that, like pollen or animal dander, something that causes an allergic reaction. So an allergen is something that causes an allergic reaction. The type 1 hypersensitivities begin just seconds after contact with an allergen. The initial contact may be asymptomatic, but it sensitizes the person, so that later, if they're exposed to that pollen again or that animal dander again, then they have a more aggressive reaction on second and third and fourth time. These reactions can be either local or they can be systemic. When they're local, it's basically it gives what you typically somebody with allergies has. They have watery eyes, runny nose, may have hives, itchy skin. Treatment for this is antihistamines. But immediate hypersensitivity can be systemic. In that case, the allergen enters the blood and circulates rapidly, and it triggers an immune response throughout the whole body. This can cause anaphylactic shock. Anaphylactic shock is basically a systemic response to an allergen. Sudden vasodilatation of the blood vessels and fluid loss from the bloodstream. That can result in circulatory shock because all the blood vessels have dilated and the blood pools and there's not enough blood to be pumped. So it actually can cause death. The treatment for this is epinephrine. That's what an EpiPen is made of. Epinephrine. It's epi and EpiPen. The epi and EpiPen stands for epinephrine. And epinephrine, is like sympathetic nerve neurotransmitter, so it's going to cause vasoconstriction of the vessels, and it's going to raise the blood pressure up. It's going to help overcome the shock that occurs in anaphylactic shock. There's a type 2 hypersensitivity. This is a subacute hypersensitivity. This is example of this is cytotoxic reaction when you're given the wrong blood type for blood transfusion. There's a type 3 subacute hypersensitivity. The example of this is autoimmune disease. This is 1 to 3 hours after exposure. So type 3 immunocomplex hypersensitivity has to do with autoimmune disorders. And type 4 is the delayed hypersensitivity. These are slow onset, 1 to 3 days after exposure. An example is skin contact with poison ivy or TB skin test. I don't know if you have a TB skin test or not, but the way TB skin test works is you're given an injection subcutaneously of the tuberculosis antigen, and then you wait 2 days and have it checked out. If in 2 days you have a reaction, then it's considered to have a positive PPD test or positive for TB exposure. It's a delayed hypersensitivity. Same with poison ivy. If you're exposed to poison ivy today while you're working in the backyard, it's going to be 2 or 3 days before you actually have a rash and itching because it's a delayed allergic response.